Hi, this is Bill, the Techno Gypsy, coming to you from the Technog Command Post. In this video, I'm going to answer the question about tiger tails, or stingers, that has been circulating in the ham community for quite some time. Do they actually work or not? This is going to be a fairly long video, as answering this question will require a considerable amount of field testing with the right equipment. This video is broken down into the following 4 parts: a basic introduction into what a tiger tail is and how it works, field testing as to whether a simple quarter wavelength tiger tail improves the radiated power of the radio, field testing between an untuned tiger tail and a tuned tiger tail, and how to tune a tiger tail to your antenna for maximum performance. So, what is a tiger tail? It is a piece of antenna wire cut to a quarter wavelength that is attached to the base of the antenna on a handheld transceiver or HT. Cutting for the lowest frequency of 144 MHz, or the bottom of the 2-meter band, this would be approximately 19 inches long. Now, let's get into a little bit of antenna theory. A vertical quarter wave radiator is essentially only half of the antenna. In order to make it work, there must be a second half that will balance the quarter wave radiator. To put it simply, as the current bounces back and forth along the radiator, the tip of the antenna cycles between holding a positive and negative charge. In order to keep the feed point electrically neutral, something else must develop an equivalent opposite electric potential to the radiator tip. This is what a tiger tail or stinger does for your HT. So in reality, a tiger tail is a counterpoise. A small vertical antenna is a non-resonant antenna. Just adding a little bit of wire does not make it into a resonant dipole. It is important to understand that radials and a counterpoise are 2 different things. Radials provide a capacitive coupling between the antenna and the earth. The counterpoise to the antenna is the earth itself. A resonant counterpoise provides the necessary balance to a quarter wavelength vertical radiator without the need for a physical ground connection. To prove or disprove that a tiger tail works, I will measure the radiated power from the HT. This is a critical performance measurement for a radio transmitter. Transmitted power can be expressed as field strength or volts per meter and is measured at a distance of 3 meters from the transmitter. Let's take a look at some of the theory behind the measurement. Don't panic. This is not going to be a deep dive into theory and math. Power transmitted from an antenna spreads out in a sphere. At any point on the surface of a sphere with radius r, the power density in watts per square meter is given by the equation PD equals P sub t G sub t divided by 4 pi r2. This is simply the power radiated by the surface area of a sphere with radius r. The gain symbol, G sub t, has no angular variation. It is often quite small because quarter wavelength antennas are not very efficient radiators. For this reason, P sub t and G sub t are taken together to mean the effective isotropic radiated power, or EIRP, of the transmitter and antenna combination. Measuring the radiated electromagnetic emissions requires a measurement system. The system I put together is comprised of a Tektronix USB 306 spectrum analyzer, a Tektronix PSM 3310 power meter, a Hewlett-Packard 1166 7B 50 ohm power splitter, and a ICOM AH8000 super wideband discone antenna at a height of 8 feet. So let's head out to the field and set up the measurement system. Whew, that was quick. Now that the measurement system is in place, all I have to do is stand approximately 3 meters or 10.5 feet away from the measurement antenna and press the push-to-talk key on the radio. The initial tiger tail is cut to a quarter wavelength, or roughly 19 inches at 144 megahertz. I tested it using 2 antennas. A Comet BNC-24 and a Diamond SRH-77CA. To help eliminate variance due to the radio manufacturer, 2 different radios were used for testing. A Waxon KG-UV8D and a ICOM ID51A. Keep in mind that the HP power splitter introduces a 3 dB loss, or halves the power, to each measurement instrument. But I am not interested in characterizing the transmitter and antenna combinations. Instead, I just want to verify whether a tiger tail actually increases the effective transmitted power coming from the radio. Does it work? A series of 8 tests were performed along with a baseline measurement to establish the noise floor. Testing was done using both antennas on a specific radio with and without a tiger tail. The power meter results are displayed in dB volts, dBm, dB microvolts, and microwatts. So, let's run the baseline measurement. The frequency of the system was set at 146 megahertz. The output from the spectrum analyzer is displayed in the upper window. The lower window is the output from the power meter. The frequency can be seen to be clear of any other transmitting devices. The baseline measurements are minus 58.128 dB volts, minus 45.118 dBm, 61.872 dB microvolts, and 30.774 nanowatts. A pretty clean test environment. The first test was done with the Waxon KG-UV8D radio, the Comet BNC-24 antenna, and no tiger tail. The test measurements are minus 17.999 dB volts, minus 4.989 dBm, 102.001 dB microvolts, and 317.071 microwatts. The next test was done with the Waxon KG-UV8D radio, the Comet BNC-24 antenna, and a quarter wavelength tiger tail. The test measurements are minus 13.698 dB volts, minus 0.688 dBm, 106.302 dB microvolts, and 853.458 microwatts. Notice the 536.387 microwatt increase. Let's switch from the Comet BNC-24 antenna to the Diamond SRH-77CA antenna. I am still using the Waxon KG-UV8D radio and no tiger tail. The test measurements are minus 18.713 dB volts, minus 5.703 dBm, 101.287 dB microvolts, and 268.989 microwatts. The Diamond SRH-77CA antenna actually performs worse than the Comet BNC-24 antenna on the Waxon KG-UV8D radio. The next test was done with the Waxon KG-UV8D radio, the Diamond SRH-77CA antenna, and a quarter wavelength tiger tail. The test measurements are minus 11.713 dB volts, 1.297 dBm, 108.287 microvolts, and 1.348 milliwatts. Did you notice a change from microwatts to milliwatts? This combination yielded an increase of 494.542 microwatts over the Comet BNC-24 antenna with a quarter wavelength tiger tail. Let's see if there's a difference between the Waxon KG-UV8D and the ICOM ID51A radios using the same antennas and tiger tail. The first test was done with the ICOM ID51A radio, the Comet BNC-24 antenna, and no tiger tail. The test measurements are minus 17.933 dB volts, minus 4.922 dBm, 102.067 dB microvolts, and 321.940 microwatts, pretty close to the test results from the Waxon KG-UV8D. The next test was done with the ICOM ID51A radio, the Comet BNC-24 antenna, and a quarter wavelength tiger tail. The test measurements are minus 18.518 dB volts, minus 5.508 dBm, 101.482 dB microvolts, and 281.315 microwatts. Much worse than just the antenna without a tiger tail. Starting to make me think there's a tuning issue at play here. I then switched from the Comet BNC-24 antenna to the Diamond SRH77CA antenna. I am still using the ICOM ID51A radio and no tiger tail. The test measurements are minus 18.335 dB volts, minus 5.325 dBm, 101.665 dB microvolts, and 293.428 microwatts. The Diamond SRH77CA antenna performs about as well as the Comet BNC-24 antenna with a tiger tail. The next test was done with the ICOM ID51A radio, the Diamond SRH77CA antenna, and a quarter wavelength tiger tail. The test measurements are minus 13.279 dB volts, 0.269 dBm, 106.721 dB microvolts, and 939.963 microwatts. Now, let's take a look at all of the results for the radiated power outputs in microwatts. This chart compares the Waxon KG-UV8D and the ICOM ID51A when using both the Comet BNC-24 and Diamond SRH77CA antennas, with and without a tiger tail. Did you notice the change from microwatts to milliwatts? This combination yielded an increase of 494.542 microwatts over the Comet BNC-24 antenna with a quarter wavelength tiger tail, an impressive 1.348 milliwatts of radiated power. But there is a very interesting anomaly in the power measurement from the ICOM ID51A with the tiger tail. Look at the red value as it shows the power output went down when the tiger tail was attached to the radio. The test results from the ICOM ID51A radio, Comet BNC-24 antenna, and quarter wavelength tiger tail combination were quite surprising. This is when I decided to dig deeper into the issue of tuning the counterpoise to the antenna. This effect is probably why some hams make the claim that tiger tails do not work. So, let's head back outside for some more test measurements. The frequency of the system was again set at 146 MHz. The output from the spectrum analyzer is displayed in the upper window. The lower window is the output from the power meter. The frequency can be seen to be clear of any other transmitting devices. The next test was done with the Waxon KGU-V8D radio, the Comet BNC24 antenna, and a tuned quarter wavelength tiger tail. The test measurements are minus 9.986 dB volts, minus 3.024 dBm, 110.014 dB microvolts, and 2.006 milliwatts. Wow! A very nice increase in radiated power. The next test was done with the Waxon KGU-V8D radio, the Diamond SRH77CA antenna, and a tuned quarter wavelength tiger tail. The test measurements are minus 11.094 dB volts, 1.916 dBm, 108.906 dB microvolts, and 1.555 milliwatts. The next test was done with the ICOM ID51A radio, the Comet BNC24 antenna, and a tuned quarter wavelength tiger tail. The test results are minus 9.184 dB volts, 3.827 dBm, 110.816 dB microvolts, and 2.414 milliwatts. Wow! Now that is an increase in radiated power. Keep in mind that all of these measurements are at minus 3 dB, or half power. The next test was done with the ICOM ID51A radio, the Diamond SRH77CA antenna, and a tuned quarter wavelength tiger tail. The test measurements are minus 10.305 dB volts, 2.706 dBm, 109.695 dB microvolts, and 1.865 milliwatts. Now, let's take a look at all of the results for the radiated power outputs and microwatts between the tuned and untuned tiger tails. So it looks like the best combination of radio, antenna, and tiger tail is the ICOM ID51A, the Comet BNC24 antenna, and the tuned tiger tail. It provides a whopping 2.414 milliwatts of radiated power at minus 3 dB. Guess I know which combination to keep in my go bag. It looks like we have found the issue with why some hams say tiger tails don't work and others praise them. Like anything dealing with antennas, it comes down to tuning. The idea that a tiger tail is a radial, or the missing half of a balanced dipole, is completely wrong. A tiger tail is a counterpoise and must be tuned to achieve maximum performance. Let's move to the bench and I'll show you how I tuned my tiger tails to both antennas. I have my Bird AT500 antenna tester with both the antenna and the tiger tail directly attached to the unit. The tiger tail is initially cut to the quarter wavelength of approximately 19 inches. The sweep frequency of the antenna tester is set from 144 to 148 MHz. Droop the tiger tail in the approximate position it will be when hanging from the radio in your hand. We can already see that it's at 1.87 on the SWR. Now, start cutting small amounts, very small amounts, drop it down, and look at the value. Going to cut again. And again. Cut again. And we keep cutting until we get the SWR dropping down to lowest value. To tune the counterpose. The final conclusions regarding tiger tails is that they are a counterpoise, and as such they must be tuned to the antenna for maximum radiated power. On the receive side, a tiger tail just increases the size of the antenna. I hope you have enjoyed this video and found the information useful. Please check out my Patreon page at www.patreon.com/technog if you would like to help support my channel. This is Bill, the Techno Gypsy, saying 7-3, and God bless.